Okay, it's 9:40, so let's get started. So, as you can see, quiz 8's out tomorrow, Saturday, usual. Homework 4 is out. The good thing about homework 4, I believe, is that you have an extra week to do the first part, and then, I guess, 3 weeks to do the second part. So, it's actually really cool. One of the first part is all about a CFG that makes postal addresses, and then you have to make convert to PDAs and all this stuff. So it's actually pretty cool. So a real life problem, actually. Okay, any questions before we start then? Anything about midterm homework 3, class material, anything? Going once, going twice. Okay, so this is probably the hardest week in all of my recitations I've ever done because I have so little material to go off of, but we'll try to fill up the full 50 minutes anyway. What was the main thing we talked about last week, I guess, in only one class? Yeah, this conversion from PDAs to CFGs. Well, what we covered last time is that we can go the other way. We can convert an arbitrary CFG to a PDA by what we did is we tried to simulate a derivation on the stack. And we did that by putting a special symbol on, then we put the start variable on, and anytime we see a terminal, we read it off the input and pop it on the stack. If we see a variable, we apply a rule derivation to get the next set of things to work with. And then once we're done, we pop off that special symbol and then we accept. But what about this way? But first off, if I can show this, then what can I claim? Given that we've shown that direction.
They're equivalent.
Yeah, they're equivalent, right? I can convert back and forth arbitrarily, so therefore we can conclude that PDAs recognize the context-free languages. But how in the world am I going to do this? I have to convert an arbitrary PDA like that into a CFG. So I got to convert these states and transitions, all this stuff, to variables, terminals, and rules, right? How in the world am I going to be able to do that? Let's see. When we did the CFG to PDA conversion, what does the stack always start out as? Empty. For this particular conversion, what did the stack end up being? Well, remember, we pushed on that special symbol at the beginning, then the start variable, we did the whole derivation using the stack, and when we wanted to accept what was on the stack, whatever the special symbol was. How do we detect that that's on top of the stack? You pop it. So we accept by popping that symbol, oh, what's the stack now? It's completely empty. So maybe if we go here, maybe we can ensure that the stack is empty when we accept using this PDA. But do PDAs in general have to accept with an empty stack? No, they don't have to, right? I can have a PDA that, for example, it just loops on one particular character and just pushes that character on the stack. So it's pretty obvious to see that this PDA only accepts strings that are entirely A's. But when we accept, we're going to have a whole bunch of things on the stack. And we don't want that to happen. Because we want to ensure that the stack is empty or has the possibility of being empty when we accept. So how do I do that with an arbitrary PDA? This may or may not empty the stack at the end. So how am I going to ensure that here? So for example, if we have a PDA that looks like this, it's not a box, but so this is a PDA, let's say. when we go to, let's say it has 2 accept states, it may have more, or fewer actually. When I have these 2 accept states, it may go into them and accept with something on the stack, right? But I want to ensure that if it can accept, there's another way to accept with an empty stack, because I want to ensure that possibility. So how can I guarantee that here? Create not a new start state. Yeah, I make a new final state. And then what do I do to hook this new final state up to the old ones? Yeah, well, I better be able to come from these, only from the final states to here. Because I want to have a possibility of accepting so I want to be able to get to here if I could accept originally, so it better have come from the final states here and nothing else. But how do I transition over to here? First off, should I read something? No, so these transitions are going to read nothing. What about popping? I mean, I could, but I want to make this as general as possible because the stack may be empty here, and therefore I can't apply that transition. I don't have to apply the transition, but I'm trying to be as general as I can, so I'm not popping. Should I push anything? I mean, the whole function of this state is just going to be looping, popping things off, so there's no reason to put something on. I mean, I could, but there's no reason to do so. Okay, then what is this state going to do? Yeah, just going to self-loop, popping everything off the stack. So epsilon A to epsilon for all A in the stack alphabet. So you may be wondering, well, you can, what you said here is that you can come here with something on the stack possibly, and you can loop here, just popping things off. What if you get to an empty stack and you are in this state? What happens? The computation has to stop because I don't have any other transition to do, right? I don't have any other transition to do. But what's something I can do to these final states here? Once I made this new state. Make them non-final. And why do I want to make them non-final? I don't have to, but I can. Because I only want to ensure when we eventually convert this to a CFG that there's only one way into the machine and one state to accept. So there's only one entry point, one state, one exit point. Whereas before I had 3 in this case. Okay? So I just want to ensure that. But is it clear why we want to empty the stack here? Because in the conversion this way, we made a PDA that did that. It seemed like a sensible idea to ensure that about the PDA we had. And the nice thing is that this works with any PDA. I didn't draw the machine itself, but this works with any arbitrary PDA. Okay. What else did we do? What else did we do to change the PDA that we had once we did this? Well, what are some, if we look at this transition, what's happening to the stack on that transition? Nothing. Nothing's happening to the stack. So when we did the conversion from PDA to CFG, what did we have to ensure about the stack on every transition? Right. Well, another way of saying that is that we have to ensure on every transition the stack height changes. It either goes up by 1 in the case of pushing, or it goes down by 1. And let's think about why we actually need that. So if we plot, say, stack height versus time, I guess. Well, suppose I fed a string that this machine accepts, let's just say. What does the stack start out as? The starts out as empty. So at time 0, it's going to start at height 0. And when it accepts, what can I guarantee about the height? Well, I can't guarantee anything, but there's one way of accepting that I can guarantee what? That the stack's empty. It doesn't have to have the stack empty, but there is a way to do so because I said the machine accepts it. Well, suppose it accepts it. What does the first transition do? What do I want the transition to do? A push, right? Because if I just had the PDA like this, I may have a transition that does nothing like this, and I don't know what happened to the stack if I looked at it like this. But if we somehow can make it so I only push or only pop, then I know exactly what happens to the stack. I don't know necessarily what symbol it is, but I know what happened to the stack. Okay, well, what about this right at the very end? What is the last transition? It has to be a pop because I can't get to 0 height with pushing, because then I would have negative height and I can't have that. Well, in the intermediary part, it may go up and down, it may do a lot of things. It may come down back to 0. Let's say it comes down once, and it comes back up, down, up, and then it does the final transition again. Okay? Well, let's see. So let's look at this middle part right here. What about the transition that got me down to 0 the first time? What do I know about that transition? Well, other than it's pop, obviously. Is there something I can guarantee about the symbol itself? I have an arbitrary PDA. I don't know what the stack first pushes on. I don't have some special symbol to help me here. Is there some other transition that can help me though? With what was popped on this transition right here? It's the thing that I pushed at the beginning, right? Because I said that this is the first time I come back down to 0. Well, the only way I can inspect the stack is by popping something. And so I can never come back down to 0 without looking at this particular character that was pushed. So the character that's pushed at the beginning is the same character as the first time I hit 0 at the end. But we gotta check. Do I guarantee I will ever hit 0? Do I guarantee that? Yes. How do I know that? Because I end up at 0 at the end. And I accepted it, which is exactly what I want. So I must be able to get down to 0 eventually. Okay? Any questions about the intuition there? Okay, well, that's nice and helpful. Maybe that could help us with the rules. But how do I know I can even get to this point? Could I convert this arbitrary PDA into something that always pushes or always pops but doesn't do both on the same transition? Could I do that? Yeah. Well, what are the 4 types of transitions? Does nothing, but pushes nor pops, pushes but doesn't pop, pops but doesn't push, or does both. I think those middle 2, the pushes but not pops and pops with no push, those ones are okay because those fit into here. So let's look at the transitions that do nothing. So if I definitely have them here so they can come up, could I model this transition as a single transition or multiple transitions where I only push or only pop on it? Could I model that? Yeah, how would I do that? Yeah, the stack may be empty right here, so I can't necessarily pop something then push it back. What I could do is push an arbitrary symbol on, then pop the same symbol off, or a different one. The same one, because I want to get back to the same place I was, so I better pop the same thing. So I better turn this into 2 transitions. And it says that I have enough. I should say that I may be able to read here. The reading isn't important. But let's just say I have reading here. Well, if I do read here, I can't read on both transitions because then I would be reading something that's not in the language necessarily. So I'm going to read on one transition. It doesn't matter which one I read on. And not read on the other one. And as we just said, we got to push an arbitrary symbol on, then pop it off. So does this first transition pop anything? No. So it's not going to pop. But let's just say I push on an X, an arbitrary symbol from the alphabet. Then I got to pop it off, the exact same symbol. And then I better push nothing because I want to end up exactly where I was. Okay? So I better not push there. Okay, does that make sense? Am I done with the conversion? No, what have I forgotten? What kind of transitions am I forgetting? The ones that do both, right? The ones that push and pop. Okay? So let's look at those. So let's say I read an A, pop a B, push a C. Okay? Well, how am I going to model this transition as one or more transitions that only do one? Which of these two operations, push and pop, do I do first? Yeah, I pop first. So maybe we can proceed a strategy that's like this, except I pop first instead of push first, then I push later, the other character. So let's model it again as two transitions. One reads, the other doesn't. Well, the first transition better pop. So I better pop that guy. And for that reason, I better push nothing. And here, I better pop nothing and push the C afterward. So a lot of the things in this class are all about simulation. So what I'm doing here is modeling these transitions as a simulation with other transitions. And once I do this conversion, I know the computation will have stack types that look like this. And therefore I can analyze it better. Okay? Any questions about how we were able to do this? So now let's actually do the fun stuff. So we actually make the CFG. So I gotta come up with variables. So what kind of variables should I be thinking in my brain as to help me here? Well, what is the language of the PDA? It's all the strings that take me from the start state to a final state or the final state. The final state, because I only have one right here. So that's going to help us a lot. So maybe we can model this as a bunch of subproblems in a sense. Well, if I want to know all the strings from here to here, if I know all the strings from here to here, do I know the strings from here to here? Yeah, because this doesn't read anything, so I just stick an epsilon on, well, not really, but if this transition happened to read, let's say, then I just stick that character onto whatever set of strings this guy has to get to here. And therefore, I just have a bunch of subproblems that I can combine to get to the one that I want. So let's make a bunch of variables that represent every state to every other state. What strings can take me from here to here, let's say. So we're going to have variables, and the convention is to use A sub PQ, where P and Q are states. So in my mind, what this representing is, all this variable itself is going to generate all the strings that take me from state P to state Q. Okay? So that's exactly what I want, but not quite. It's always not quite here. But what other property do I want about the strings in terms of the PDA itself? And it has something to do with the stack height. When I get from state P to state Q, well, for example, the start state and the final state here, what do I want to know about their stack heights?
They're equal.
That they're equal. So, in a sense, this represents all the strings that take me from state P to state Q, starting with an empty stack, ending with an empty stack. It's not necessarily empty, but in my mind, it's not going to dip below wherever I started from. So in a sense, it's an empty stack to empty stack. Okay, well, an easy one is, what is the start variable? Well, the start variable is the variable that's going to generate all the strings in the grammar's language. So which variable should I pick here? Well, it's going to be a of something, right? But what are the two subscripts going to be? From where to where is the language of the PDA? The start state to which state? The single final state. Ah, that's nice. So the reason that, so if I say Q0 is the start state, QF single final state, by making sure that this was the only state that accepts, therefore I can make a single start state like this, okay? Because I know there's only one entry point, one entry point. Okay, so, and we know the terminals of the grammar are just gonna be the input characters in the PDA, so we're fine there. So now all we have to do is to make the rolls. Okay, how are we gonna do this? So what we need to figure out is, how can I get from some state to some other state? And one easy case is, I gotta get from state, let's say P, and I gotta go to state P. So, now, this variable may generate something else than what you may expect. It may go in a loop and come back and generate something. But what do I guarantee this variable makes? Epsilon, right? Because I know that if I read nothing and basically do nothing, I don't leave the state, so therefore I can generate epsilon. I don't have to take any epsilon transitions. So I know this variable can make epsilon. It may make other things, but it makes that for sure. Okay, well, let's see. We might have a situation like this, where it goes up and comes back down, back to empty stack. And then from an empty stack, it goes back up, comes back down to empty stack. That may happen, and it does in this picture. So how am I going to relate that? Well, let's say that this is state P that I start in, or any general state, actually. Let's say that that's Q in the middle, and this is R over here. They may all be the same state, they may all be different states. But I want to be in general here. So how am I going to relate those variables to each other? I want to figure out what A sub PR is. I want to figure out what all the strings from P to R are. Well, could I use Q to help me here? Yeah, how can I do that? Yeah, so what this is any string that takes me from here to here surely is of the form some string from P to Q concatenated with some string from Q to R. Could I represent that as variables? Yeah. So any string that takes me from P to Q concatenated with A sub QR. So this is for all P, Q, R estates. Okay? That's just the intuition. If it does come back down to 0, then if I know the two sub-problems, do I know the whole thing? Yeah, it's just concatenation. Okay. Well, I hope this is not the whole grammar. Because if this is the whole grammar, what string can I make? The empty string. And that definitely is not what I want. So I gotta look at the transitions themselves. Well, what we said is that this push is corresponding with the first time it comes back down to empty stack. So let's see. So let's look at the transition blown up, I guess. I'll make it a little bigger. And there's some stuff in the middle. Comes back down. Comes back. Well, I'll keep with my notation. This is state P and Q right here. And these two states in the middle that I go to, because they are transitions, they may be completely different, but I'm just going to call them R and S to be in general. Well, let's see. This push, whatever I push, corresponds to this pop. So let's say that I push an X right here. Do I pop in this transition? Nope. So I know what that is. For this one, what do I pop? X. But I assume that this is the first time I come back down. So I pop X. Do I push anything on that transition? Nope. Do I require anything about what happens on the reads here? Not necessarily. They may or may not read something. So let's say that this one, for instance, reads an A. This one reads a B. If I somehow know what happens from R to S, do I know what happens to P and Q? Yeah, how are those related? Well, let's see. I want to figure out what PQ is. So A sub PQ, that's the guy I want to know. If I know A RS, do I know A PQ? Well, let's see. How do I get from P to Q? Well, one way is to go from P to R. Any string that R can make go into S, then go from S to Q. Well, what do I read on the first transition? An A. Concatenated with anything that takes me from R to S. Well, what is that? How do I get from R to S? ARS. I assume I know the subproblem, so we're good. From S to Q, how do I get there? Reading a B. So, if I know the subproblem, I can know the larger one. So all this really is, and it wasn't really emphasized, but the whole idea is a bunch of subproblems, and we just connect them this way. Okay. Any questions on how we were able to do that? I know it's a long conversion, but okay. So let's get to the fun stuff. Well, I think it's all fun, but an actual example. All right, so here's a PDA, and I want to convert it to a CFG. So what is the first step that I need to do? Well, there is one final state, but is there a read transition on that final state? Yeah, there is. The self loop reads a B on the transition. Could I have a self loop on the single final state here that reads something? No, I can't have that. So I have to make another final state. Well, make a single other final state. So I gotta modify my P. I'll just do it in place, I guess. So I gotta modify this so that this guy better not be the final state because I better have a single final state. And how do I get from, I'm gonna call it Q3, that's final. How do I get from 2 to 3? The triple epsilon transition. Good. So epsilon, epsilon goes to epsilon. And then what's Q3 gonna do? It's going to self-loop on every stack symbol. Well, it wasn't told to me what's the stack, symbols. So let's say that it's just A, B to be simple. So what do we do here? Well, it's self-loops, but what are the transitions themselves? Are these transitions going to read? No, so better not read on those. Are these transitions going to pop? Yep, and they're going to pop each of the characters, so one does A, one does B, and it's pretty obvious that I shouldn't push on either. Okay, that part was pretty easy. Any questions on that? Yeah.
Yeah, so you say that we're looking at plastic, you can't move on the plastic, and
No, I can't loop on a transition that reads something. Yeah, I have to do this, but I can't, if it was, say, epsilon like this, then I could leave this and add an epsilon b to epsilon here in place, but I want this to work for any PDA, and this one I have to do it, so it's always a good idea to make a new constant. Yeah.
Since we don't know what the empty stack symbol is, would the create form for this?
I won't, because once I'm in this final state, once the stack actually is empty, I can't apply a transition.
Okay.
So I'm forced to stay there. Yeah. Okay, any other questions? Okay. So, is the PDA of the form the one that I want? Or are there transitions that are not good here? Well, I think it's mostly good. So this one pushes but doesn't pop, pushes but doesn't pop, pops but doesn't push, pops but doesn't push. Oh, this one's a problem, but these two aren't a problem. So we're almost there. That's good. So this is the only guy that I need to fix. So again, I'm going to do it in place. Let's take space. So I'm going to definitely delete this transition. But what am I going to do? I better make another state, so I'm going to call it Q4. And then what transitions am I going to add here? Should either of these transitions read? No, because the original transition didn't read, so both of these better not read, because I'm just trying to simulate here. So I'm definitely going to go to Q4 from Q2, 4 to 3. So definitely not reading on either transition. What about popping? I pop from Q4 to Q3, but what do I pop? The thing that I push. So I gotta decide what thing I'm gonna push. So let's say, and I'm definitely not popping on this one. So let's say I push an A because it's one of the stack symbols. I can choose arbitrarily, but I better choose the same one on the next transition for popping. Okay. And now our PDA is in the form that we want. So that's really nice. Okay. Any questions on that? Okay. So now I want to convert it to a CFG. So what do I do first? What are the variables? The states, but can you give names to the variables? Yeah, so it says that for every 2 choices, could be the same, in the set of states, then I better make a variable for them. Well, I have 5 here, so that means I'm going to make 25 variables. So I'm not going to write every single one out, but the variables are going to be, so A, Q0, Q0, A, Q0, Q1, all the way to A, Q4, Q. It'll be pretty evident right away that we shouldn't do this by hand. We should make a computer do it. And a computer can do it too. So that's good. So I have I have 3 of the 25 variables listed, but I will have 25 variables. The terminals are I should write it down, is A and B, because it's just the stack symbol. It's the input characters here. It just so happens that this PDA has the same stack alphabet as the input alphabet, but it's just entirely a coincidence. Okay, well now I gotta, first off, what's the start variable? Well, it's start variable. Well, the one that we had here was Q0, QF. So the final state, there's only one here, is Q3. So the start variable is Q0, Q3. Because I want all the strings that take me from 0 to 3. Yeah?
Wait, why do you have a Q4 when Q4 doesn't move to itself?
I'm blindly making all pairs here. First off, so this is really for the question on the back of the sheet. What about this variable? It's definitely going to be in my set of variables, but will this variable ever do anything? No, because there's no way to get from Q4 to Q2. So we definitely will make a bunch of variables that make no sense and a bunch of rules that make no sense. But I want this to work in general for any PDA. And if you can think about if you have a PDA that you represent as a directed graph, if it's a strongly connected graph, then every single variable will be necessary. Because from the start variable, you can get to every other state, from the start state, you can get to any other state, and from any other state, you can get to any other. So this one's definitely not a strongly connected graph, so I will have variables that don't make any sense. Okay? Any other questions? Okay, so that's just my start variable. So now I gotta make the rules. So what are the easy rules? Well, I think the easy ones are these ones, right? So because from any state, if I don't do anything, then I've read nothing, so therefore I produce the empty string. So Q0 produces empty. I'm not gonna write all of them, but Q1, empty. I'll just write the last one. Q4 produces empty. Again, much better for a computer to do. Okay, well let's see. What's the next set of rules I have to apply? It's like 10:15. What is the next set of rules I have to apply? Right, the ones that take me to this middle point right here, right? So it says that I need to do this for all three choices of states. So how many rules will I make using that method? Or this set of rules? Well, 5 states times 5 states times 5 states. I think that's 125 rules. So I'm definitely not writing them all. But let's see. Do I impose anything about what P, Q, and R are? Other than the fact that they're states? No, I don't assume anything because not in this particular case, but it may be possible that I can go out and come back to from Q2 back to itself with an empty stack, then go to Q3 with having an empty stack. So I need to handle all the possibilities of empty stack to empty stack in the middle to empty stack at the end. So in this case, I can make optimizations, but I'm not going to assume this in general. So let's see. Suppose, for example, that I'm going to write down my P, Q, and R. Well, since they're arbitrary, let's just say I have Q3 and Q1 right there. Since they're completely arbitrary, what rule will I make with this? Well, the thing I gotta start from is Q0. And the thing I gotta get to is Q3 because that's R. The thing I wanna get to is Q1. Well, what do I better produce? Empty stack starting at P, intermediary empty stack at Q, then I still end up with an empty stack at R. So how do I write the right-hand side here? Well, from P to Q, what is that? AQ0, AQ3. Q0, Q3. And the key here is concatenation. So concatenation with getting from Q to R. So from Q3 to Q1. So big Q3. So a common mistake I've seen is that when students are writing these all three choices of states rules like this, they mess up the fact that these two coordinates down here have to be the same. Because if I go from empty stack here to empty stack here, I better start in the exact same place that I was and empty stack over there. And these two coordinates have to be the same, these two coordinates have to be the same. But other than that, it has to work. I have to do this for every single three choices of states. Okay, well, let's just assume I did all other 124 rules. What do I have to do next? Well, what I got to do is the third set, right? Where I read something corresponding to pushing a symbol and then popping the same symbol off on a different transition. Do I assume anything about where these two transitions are other than that the fact that the first one pushes a symbol and the other one pops the exact same thing? Do I assume anything about where those transitions are? What's that? Other than the fact that they match up. No, I don't assume anything. These could, P and R could be the exact same state. They could all four be the exact same state, possibly. But I want to work this in general. So here what I gotta do is, whatever symbol I gotta look for, let's say I'm pushing an A here, I gotta look at all other transitions that correspond to popping an A, okay? So let's say I'm looking at this transition right here. So here I have Q0, A, epsilon A. So I gotta look for some other transition that pops an A. Is there one? There are actually several. Here's one that pops an A. This one pops an A. And this one pops an A. Okay? Do I have to do a rule for each one of those? Yeah, just to be completely complete, I guess. Completely complete. All right, so let's look at, say, Q2's self-loop, because that will be actually the most interesting one. But I have to do this for all possibilities. So let's see. Which one is the push transition of those two? Yeah, Q0 is one, so I'm just going to make a note that this is the push, and it looks like this one's the pop. That's pretty simple. So it says that this is the push guy. So what do I know about P and R right now? Remember, this is the push transition. So from where to where did I go on the push? Q0 to Q0, so I think both of these are Q0. And similarly, S to Q is popping the same symbol, well, we got that. So I go from Q2 back to itself, so Q2 to Q2. So I think S and Q are both Q2. So S is Q2, Q. So I like writing those four out because it makes applying this rule so much easier. Well, what does it say? It says A sub PQ. Well, P and Q are Q0 and Q2. So I'm going to make a rule Q0, Q2. Well, what is the guy in the middle? RS. Well, R is Q0, S is Q2. So the guy in the middle is also Q0, Q2. But do I read anything on the push transition?
Yeah.
Yeah, I read the symbol A according to the transition. So at the beginning, I better read an A. What about popping? Do I read something? Yeah, I read a B. So I put a B over there. So it may be possible that one or both of these are empty. Actually, we'll do an example of that, but I want this to work in general. So let's do same transition over here, but the Q4 to Q3 one. So I guess I'll do it right here. So Q4, Q3, which is the final state, and I have epsilon A to epsilon. So I have the starting transition being exactly the same, so I'm not going to modify this. What are my S and Q going to be right here? So from where to where did I go? Q4 to Q3. So what's S going to be? Yeah, the one I started with, which is Q4, and Q, which is Q3. So I'm going to make it go like this. So let's see. A sub PQ, well, what is that? That's Q0, Q3. So I'm going to make a rule A, Q0, Q3. Well, what's the right-hand side? It's, let's do the middle part. ARS, what is that? ARS, what is that? Q0, Q4. Okay. Q0, Q4. On the push transition, did I read something? Yeah, I read something just like we did before, so I better put an A right here. On the pop transition, did I read something? No. So now I'm not going to actually put anything right here. And therefore, we're done with that rule. Okay? Cool. Any questions? And then we obviously continued this for all possible choices of pushing some symbol, one of the two symbols, and popping the exact same symbol somewhere else. Okay. Any other questions? Okay, so I don't think I'll be able to start the next one, but are there any last minute questions about this or anything? Let's see. Actually, I'll add one last minute question. When we converted it to here, why did we insist that the stack has to change? Why don't we just look at the stack type when it's even, when it stays the same? Because if I have a transition that doesn't push or pop, or does both, then the stack height will stay the same after we apply the transition, right? So why don't I allow that here?
This would be ambiguous.
Right, it actually could be ambiguous. We'll consider a transition that does stay the same and then does whatever. What do you know that you did on that transition? Do you know if you did both operations or did none? No, I don't know anything about that. So the reason we do it this way is that we can ensure the fact that, did it the other way, is that we know exactly what happened on the transition. And therefore, we can guarantee that the stack will be empty. Any other questions? All right, I'll see you next week.